In this lecture, we will derive an expression to find the energy density in an electrostatic field. So you've seen that the energy stored in a given configuration of charge is given as rho the potential dV dash over volume V dash. Now this rho is the free charge, and by Gauss law it is equal to del dot D. So I will put it as W is equal to half of del dot D V the potential dV dash over volume V dash. Now WE can be written as half of del dot D. Now V is simply minus of del this E is equal to minus of del V. We will try to utilize it somewhere. Now how to do that? Because we need to find the energy in terms of the field quantities. How to do that? Now you see that del of some scalar into vector is given as del k dot A plus k del dot A. So it implies del dot some V into D is equal to del V dot D plus V del dot D. Now this implies this V del dot D is equal to del dot VD minus del V dot D. So I will now use this equation in this integral. So WE is equal to half of integral over full volume V dash del dot VD dV dash, or I will take it outside, minus del of V dot D dV dash. So we will now further expand this bracket. So total energy is equal to half of del dot VD dV dash over full volume V dash minus half of D, what was the equation, dot del V dV dash over V dash. Now in this we will use the divergence theorem. We will convert it to surface area. Half of V D dot ds over surface S minus half of D dot, now I will take this minus sign inside, minus del V dV dash over full volume V dash. Now I will assume that this volume V dash is covering whole of region, that is up to infinity. So it implies this surface is also up to infinity. So you see that V varies with respect to 1 by R, and D varies with respect to 1 by R square, and ds varies with respect to R square. So VD ds will vary at least with respect to 1 by R cube into R square, that is 1 by R. So when this R tends to infinity, this surface integral will go to 0, because we want to just evaluate it on the surface, on this surface only. So on this surface this integral will be 0. So only thing remaining will be this integral inside this whole volume. And since we are just integrating over the sources only, so we will have to just integrate over the sources only. The other part there will be no source, so the integral will be 0 in other part. So W is simply half of D, now minus del V is equal to E only dV dash over full volume V dash. So energy per unit volume is simply half of D dot E. So this is the energy density in electrostatic field. Now at least for electrostatics, no one knows where this energy is stored, whether this energy is stored in the charges or in the field, no one knows. But it is one thing clear, is that you can find the energy just by integrating this quantity in a given volume. So although it is not clear where this energy is stored, but at least in electrostatic field, but we can find the energy by this integration. When we will study that phenomena of wave propagation and everything, then we will try to see that this wave propagation. In wave propagation, the energy is sometimes thought of being contained with the field itself, the electric and the magnetic field itself. However, for electrostatics, it is not clear because there is no kind of wave motion, nothing, so no one knows where this energy is being stored. But people still think that this energy is stored in the electrostatic field, and we can calculate this energy by just calculating this integral in a given volume. So in this way, we can calculate the potential energy stored in an electrostatic field, and this is the energy density. That is energy per unit volume is half of d dot E. So if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group whose link is given in the description of this video. Thank you.